Okay, you can play with that one as well. You can see how can you change it. But for now, I'm going to switch to the distance-based model. One of the straightforward model whenever we are talking about distance-based model is k-nearest neighbor. So it means if you have a function that given a point, you can compute the top k point similar to yourself, and then you can say, so in supervised model, they're saying that each sample has a label, and then by computing k-name, they're saying that what is the label of my k nearest neighbor, and then based on that, they're pointing a label. Here we don't have a label. The thing that we care about is actually the distance. So we are computing the distance to the k nearest neighbor to yourself, and then we say that that distance will say how far you are from the rest of the data. So here is a function that you can read. It will compute the k nearest neighbor, and then for finding anomaly, here I'm just using that function will just use the data, the k, and the threshold. The threshold will say how far, like the distance is like if the distance is more than that threshold that you're defining, that's fraud. Whenever you're talking about k-name here, there's a two-way of measuring the distance. Sometimes you can say, okay, if k is 10, you're computing distance to the 10 nearest neighbor. Then you can do average, or you can just say which point is the one that has the highest distance to me, or you can just use that distance as a score. So that's why here I'm just computing both of them. The first one, the thing I'm returning is the distance to the one which is far from you, and the average one is your average distance to all those points. So as an exercise, you can try different k and threshold to see their effect here. Then which one is the student one? Okay, this one is student one. Just want to see if you have it or not. Okay, you don't have it, so you can compute it. But if you want to cheat, that's the code. But per cluster, you can use different k or different threshold, and then you can compute a score. You can do that yourself if you want. Because everyone exhausted at this point. Yeah. Okay, then no exercise. Okay, so I'm gonna just talk about it, and then you can maybe have it as your home exercise if you want, and then over Slack or whatever we can talk about it and we can discuss it. So the thing here is like that. The thing that is important for k-name is the k, which is what is like how many points that I'm looking for to see in my neighborhood, and then the other thing is a threshold. What is the distance? That would be important because then it would say that what is anomaly, because it's like a threshold that we use for the GMM. Here is a distance because of distance-based model. And if I do that for those three data set, and then if I just use the case and then a score, which means the distance to the one which was further from me, that would be the one. I can play with the threshold. So here the threshold was like a small maybe for that one, but then you can see what will be the effect of the threshold when I'm finding this point. Let me make this score to be a bit smaller. Maybe for just want to show you that what will k-name do here. So here it will just all of them are anomaly, but I just want to make it to be, let's say, let me try. So 9. Or this means what was the average one as well? Okay, that was the average one. But okay, you can play with that with the k and the threshold. But the thing I was trying to say is like that. Canyon, because it's using the distance. Remember when Emerson talked about that if they are connected to each other, GMM won't be able to handle them. The distance-based model will be able to handle them. So it means here, if I have a threshold, the model should be able to say, okay, these are normal, all the rest are not normal. Even if you are in the middle, you are not normal. And if I play with the threshold, I can have different distance, but the distance-based model should be able to capture. See, you can just see here, I just use one model, same distance for all of them, same distance, same number of k. I'm not doing that. Okay, I just changed it to 9, but it actually is 4 because I haven't applied that. But you can say even using the same hyperparameter, the technique was a lot better than GMM because based on the distance, it can capture different type of, it can capture different kind of complexity in your data set.
So the 3 different ones are, what is the difference? Like, so when you say the parameters are the same, so what is the one that is changing?
Here is just, is not, okay. Pair point, I'm looking, it's like here, I'm just looking at the 10 nearest neighbor, and then I'm just computing distance. If the distance is more than 0.4 here, I will say that's anomaly.
Doesn't this have a big problem that anything on the edge of any well-defined distribution is going to end up as an anomaly?
As if there is, okay, that's why the k is important. If the k is like, if you set the k to be, let's say 100, then you will have enough point close to you that you can say, okay, maybe you're not anomaly or not. That's why here finding the correct k and the distance is important. So it is more of a density, not, you can, yeah, kind of like a density problem as well. So even if you're far from the norm, but you have your own cluster, if the cluster is big enough, bigger than the k, all of you will be normal. But if that small cluster at the very end of your tail is less than k, then all of them will be like an anomaly for you. So that's why it's like computing the distance to all the nearest neighbor. It doesn't care what is the distribution of data, where all the data like is. You just look at the nearest neighbor, compute the distance. If you don't have, if in the k nearest neighbor you don't have enough data that the distance is lower than the threshold, it will say this is from.
So then will you say this method is a local method, but then the distribution method is a global method?
No, this is global actually.
Oh, this is global.
Yes. So I'm going to jump to the local one as well. The difference between local and the global one is in the local one, it won't just look at the k nearest neighbor and say if the distance is more than something, this is fraud. It would just say what is the relation between them. It's like, see, you can say that maybe that sample here for the model is normal because maybe the k was super small, and based on the based on the relation of the density. It's like if all the points near you are sparse, then maybe being sparse in that area of the space is normal. But if kind of you are surrounded with all the points, which all of them are like super dense, then even being close to it you might say that okay, that one maybe is not normal because if you look at the k nearest neighbor, the ratio of density is super high. They are dense, you are not, then you are fraud. So the difference between the normal KNN and the LOF technique is KNN is like a global, just looking at the distance of the model to the rest of them. It doesn't care where are you in that space. The local one will look at the neighborhood and will compare the distance to your neighborhood with the distance of neighborhood of those neighbor point as well. So it's like a ratio of the density.
MNIST doing? To have like several centers, right?
The KNN will just compute the distance to, as I said, to all the neighborhood. It won't care what is the density of those neighbor point. It will just compute the distance. This one will say what is the distance to the neighborhood, and then we'll go to all those neighbor point as well, compute the kind of the same thing as well. What is the distance to all those neighbor, and they will say what is the comparison. If all the point are sparse, then we'll say maybe being sparse is not weird here. Maybe it's normal. But KNN won't care. But if you're, so it means based on the region that you are, that local one will capture different things. That's like the main difference between these two.
So since we are 3 minutes over, can we just wrap up quickly and then we can have the discussions offline?
Sure. So okay, then we can have the actual data as the bigger exercise, because then I try to put everything here as well, so you can actually see that and play with that data in your home, which means that's a credit card fraud detection. I just described it. This is like a real data set captured in 2013. It has you can see how many dimensions it has, and then you can see what is the ratio, because it does have a label. You can see what is the ratio between the normal one and not normal one. So that's like a real data set. So you can say it's like a super imbalance. So if you want to do any kind of supervised technique, you can do it, but it's challenging, and then you can actually compare, see what is the difference between them. And then if you want to visualize some of these and compute a histogram, paired normal data and for fraud data, you can even put all those features that you want here, and then you can run it, and then you will see the visualization. So it means you can sometimes use a historical model or Gaussian model, but sometimes they're exactly the same thing. So it is not different. So not all the dimension will be helpful for you. And so for your exercise, you can apply this technique on this data set. So here I just use LOF, which was the local one, using some parametric, and try to find the fraud, and to be able to compute the F1 score, recall, and precision for it. You can try the actual KNN or the GMM, and because here we have a label, you can actually compute what is the performance of the model. Because for the other one, we are saying that, okay, is it too far, is it not? Visually, we could say, but usually when we are talking about like a more complex data set, there's no easy way of saying what if the model is correct or not. Because like if I say, oh, these 10 are anomaly, how do you know, do you have any more anomaly? Because you can't see them, it's like super complex. That's why here we'll use some label data as well, because we want to compare these techniques. So you can just use these accuracy metrics here to be able to compare this model. And the other one is MNIST that you can load. I didn't do it that much here, but that's going to be your own exercise that you will remove one of the number like 7 from it, and then you will try to apply this technique. In next week, we will have more discussion about more machine learning model, like 1SVM, isolation forest, even clustering techniques, and then we'll apply them on this data and more data set for sure. Then you should be able to see on the real data set what is the performance of this model. And we can wrap it up. That's
All right, can I borrow the microphone again? Thank you.
Oh, yes.
Thanks. Thanks, everyone. Hope you had fun. Please don't close your laptops yet, because you're going to do the survey before you close it. And online people also, please do the survey so that we know how you felt about this session and we can make it better.
Yes.
We are good at making these things better. So please provide your feedback. The survey form is on Slack. So please take a look at it there. And that's it. See you.
Thanks.